Hello, my name is Dr. Garuma Abdisa, and in this specific tutorial we will cover the lens equation. Thin lenses. The most familiar and widely used optical device after plane mirrors is the lens. A lens is an optical system with two refracting surfaces. A thin lens has two spherical surfaces, close enough together that we can neglect the distance between them, which is, of course, the thickness of the lens. If you wear eyeglasses or contact lenses, while reading, you are viewing this world through a pair of thin lenses. These are two spherical surfaces, and this is a lens, of course, which is a thin lens, and the thickness is negligible. This thickness is the distance between the two spherical surfaces. There are various types of lenses. There are converging lenses, such as the meniscus, plano-convex, double convex, and on the other hand there are also diverging lenses. This is a meniscus diverging lens, a plano-concave, and a double concave. The thin lens formula. Let us begin with converging lens. Consider this arrangement for a convex lens, that is a converging lens. From this figure A, triangle ABH and triangle EBD, these highlighted triangles are similar triangles. Consequently, because the ratio of corresponding sides of similar triangles must be proportional, we can write ED over AH is equal to BD over BH. But ED over AH is simply the image height I divided by the object height O, I over O, and the BD over BH is equal to simply SI over SO, and you can refer to this diagram, and we will hold this as equation 1. Similarly, from figure B, triangle JBF is similar to triangle EDF, which are highlighted in this diagram. So, because the corresponding sides of similar triangles have to be proportional, in this case we can write ED over JB is equal to DF over FB, which implies that ED over JB, which is the image height I over object height O, and the DF over FB are correspondingly SI minus F divided by F, where SI is the image distance and F is the focal length. We will hold this as second equation, equation 2. After combining equation 1 and the equation 2, we can simply write SI over SO is equal to SI minus F divided by F. By rearranging this equation, we can finally write as 1 over F is equal to 1 over S naught plus 1 over SI. This is a converging lens formula. Let us see properties of light rays in converging lens. This is a converging lens. Let us call the left focal point 1, and the second focal point 2. This ray, which is coming parallel to the principal axis, passes through the second focal point. So, parallel incident ray refracts to pass through the second focal point F. This is one of important properties of light rays in a converging lens. Secondly, any ray passing through the center of the lens does not deviate appreciably. They almost pass straight unrefracted. Thirdly, a ray which is heading through the first focal point F emerges being parallel to the central axis, which is the principal axis. Properties of light rays in a diverging lens. This is a diverging lens. Let us call the left focal point 1, and the right focal point 2. This incoming light, which is parallel to the principal axis, is refracted as if it is originally coming from the first focal point F. Secondly, a ray which is through the center of the lens does not deviate appreciably. And this ray headed at the first focal point F, emerges parallel to the principal axis. Let us see the thin lens formula for a diverging lens. This is a diverging lens, and our objective here is to derive lens equation for such diverging lenses. So from this figure A, triangle ABC, that is this triangle, is similar to triangle DEC, that is this triangle. From this similarity, we can write the ratios DE divided by AB is equal to DC divided by AC. But DE over AB is equal to I divided by O. That is the image height divided by the object height. But DC divided by AC is simply SI divided by S naught. We will hold this as equation 1, and by continuing to the second part of the problem, that is figure B, from figure B, triangle FGH, that is this triangle, is similar to triangle FKJ, that is this triangle. And from that, we can write KJ divided by GH is equal to FJ divided by FH. From that, we can write I over O, F minus SI divided by F. That is the focal length. After combining equation 1 and equation 2, we obtain SI over S naught is equal to F minus SI divided by F. And after rearranging these equations, we can finally write minus 1 over F is equal to 1 over S naught minus 1 over SI. This is diverging lens formula. So this is for a convex or converging lens, and this equation is for concave or for a diverging lens. Once again, notice that except for the signs, the two equations are the same. This difference in sign alerts us the fact that the image in case of a concave lens is behind the mirror rather than in front of it. Also, the negative focal length term is the result of the lenses being concave rather than convex. So, once again, rather than remembering the two lens equations, we can set up rules that allow us to use one formula for both of them. Hence, we can write for all lens situations, at least for all thin lens situations, that 1 over F is equal to 1 over S naught plus 1 over SI. Here is a sign convention for lenses. We can make the following convention on the signs to be used for the focal length F, distance of the object S naught, and the image distance SI. Firstly, the object distance S naught is positive if the object is in front of the lens, and negative if the object is behind the lens. Secondly, the image distance SI is positive if the image is formed behind the lens, that is a real image, and negative if the image is formed in front of the lens, that is a virtual image. Thirdly, the focal length F is positive for a converging lens and negative for a diverging lens. Let us see magnification in terms of lenses. Magnification is once again defined as minus SI over S naught is equal to minus HI over H naught, in a similar way as that of mirrors. If M is positive, the image is upright or erect. If M is negative, the image is inverted image. If the magnitude of M is larger than 1, it is enlarged or magnified image. If the magnitude of M is less than 1, the image is diminished. If M is exactly equal to 1, it will be the same size as in the object. Let us see some image characteristics of a convex lens. If the object is at infinity, this ray converges to the focal point. This ray once again converges to the focal point. This ray also converges to the focal point. So the image is created as a focal point, and this image is point-sized image as a focal point. Secondly, when the object is at 2f, if we place the object here, this ray is refracted passing through the second focal point. This second ray passes through the center, passes straight, unrefracted, and this is the place where the image is created. And that image is real, is inverted, and it is same size as the object. And it is created at 2f. Thirdly, when the object is between 2f and f, in this case the object is between 2f and f, so this object, this ray passes through the second focal point, and this ray passes straight through because it is passing through the center of the lens, which is unrefracted. The image is created here. The nature of this image is that it is real, it's inverted, it is enlarged, and it is beyond 2f, as you can notice from this diagram. Fourthly, when the object is exactly at the focal point f, when we place the object here, what happens is that this ray is refracted through the second focal point. This ray just passes straight through, and the nature of the image is going to be infinitely big image, and it will be created at infinity. Fifth, when the object is between the focal point f and the lens, whenever we place the object here, this ray is refracted passing through the second focal point, and it appears as it is coming from that point, whose extension is shown in this yellow color. And this ray passes, because it is heading towards the center of the lens, it passes through unrefracted. All of them appear as if they are coming from this point, and the image is created over there. And the nature of that image is virtual, it's upright, it is enlarged. Now let us move on to the image characteristics of a concave lens. And this is a concave lens. If we place the object here, this ray is refracted as if the ray is originally coming from the left focal point, that is from that point. And this second ray is once again refracted, being parallel to the principal axis. So this ray passes straight through this concave lens because the ray is passing through the center of the lens. So this is where the image is created. And the nature of the image is always virtual, upright, diminished. The following general observations are helpful when dealing with lens problems. When we generalize, the first is a diverging lens, that is, a concave lens always forms a virtual, upright, reduced image of a real object regardless of where the object is placed in front of the lens. Secondly, a converging lens or a convex lens always forms a real inverted image of a real object if the object is placed outside of the focal point of the lens, or if the object is inside the focal point, a virtual upright image is created. Examples. Let us concretize what we have seen so far with examples. The first example being shows that the lens and the mirror equations can be expressed in an alternative form as where P and Q are the distances of the object and the image from the focal point F. Solution: consider the convex lens that we have already used. So in this case, the object distance is measured from the focal point F to be P rather than from the lens, which was from the lens it was S naught, but now from the focal point it is P. The image distance from the lens is SI, but now from the second focal point it is simply Q. So in this case we wanted to derive an alternative length formula, not in terms of S naught over Si, but in terms of P and Q, which are measured from the focal points. So from this figure A, triangle ABH is similar to triangle EBD. Those are triangles shown, highlighted. So because the corresponding sides of these similar triangles must be proportional, I over O, that is ED over AH, is I over O, and the BD divided by BH is F plus Q divided by F plus P. And we will hold this equation as equation 1. From this second arrangement, from figure B, triangle JBF is similar to triangle EDF. From this once again, from the ratios of the sides, ED over JB becomes I over O, and the DF over FB becomes Q over F. We will hold this as equation 2, the second equation. Remember that I over O is F plus Q over F plus P from the first equation, and I over O is Q over F from the second equation. This is equation 1, and this is equation 2. And equating them together, we can simplify F plus Q over F plus P is equal to Q over F. And by cross-creasing and multiplying them, we can reduce the equation into PQ is equal to F squared, where S naught is F plus P, and Si is simply F plus Q. This is an alternative form of length or mirror equation where Q and P are measured from F. Example, second example, an object is 5 cm in front of a convex lens of focal length 7.5 centimeters, and the problem says determine the position and magnification. Solution is S naught is 5 centimeters, F is 7.5 centimeters, it's already given, Si is required. We have this general formula for a lens, and by directly substituting and solving for Si, we get Si is equal to minus 15 centimeters. The magnification is minus of Si over S naught, which is plus 3. Because Si is negative, the image must be virtual. Because magnification is larger than 1, the image is enlarged. Because magnification is positive, that is positive 3, the image must be upright. And you can compare this with the case where the object is between F and the lens that we have seen previously, if this is consistent or not. When the object is between F and the lens, we already saw that when the object is here, this is our reconstruction, and this is where the image is created, and we have said this kind of image is virtual, upright, and enlarged, which is exactly consistent with our mathematical solutions. The second method, using the alternative length formula, still keeping S naught to be 5 cm, F 7.5 cm, and Si is required. We have S naught is equal to F plus P, and Si is F plus Q. Because S naught is F plus P, we have P is equal to S naught minus F, which is 5 cm minus 7.5 cm, which is minus 2.5 centimeters. We have the alternative formula for length, which is PQ is equal to F squared, from which Q is F squared over P, which is 7.5 centimeters whole squared divided by our P, which is minus 2.5, from which we get minus 22.5 centimeters. So because Si is F plus Q, we have 7.5 centimeter plus minus 22.5 centimeter, which will give us minus 15 centimeters, which is exactly the same result as we have calculated using the other length formula. The third example, an object 5 cm high is placed on the principal axis 10 centimeters away from the optical center of a diverging length of focal length f is equal to 5 centimeters. Determine the position and magnification. We are given that S naught is 10 centimeters, f is minus 5 centimeters, and Si is required. By directly plugging in what we have here and calculating for Si, we get minus 3.33 centimeters for the image distance. Magnification is minus of SI over S naught, which will give us plus 1/3. Because SI is negative, that is minus 3.33 here, the image must be virtual. Because magnification is less than 1, because 1/3 is less than 1, the image must be diminished. Because magnification is positive, that is plus 1/3, the image must be upright. And we can once again compare our result with, whenever the image is here, we have already seen that the image created is always here, which is virtual, upright, and diminished, which is very consistent with what we have seen mathematically.